Okay, this is going to be the first video for chapter 4. Now, chapter 4 is all about reactions in aqueous solutions. And that basically means what happens to different substances when we put them into water. Does a solid form? Do gas bubbles form? Is there some kind of temperature change? Or does nothing happen? So throughout this chapter, we're going to explore all those different possibilities. Now, chapter 4 introduces a lot of new concepts. But your ability to be able to understand and do those concepts is dependent upon having learned material from chapters like 1 and 2 really well. So there are some skills from earlier on in the semester that you absolutely need to be rock solid with before you could get started with chapter 4 material. If you don't know those things and you're really not comfortable with those skills, then this chapter is going to be really difficult for you. So what I've done is I've put together a list of a couple of skills that I think are of key importance to get started in chapter 4. Now, again, this is not a complete list. There are other skills that I don't have written down here that will be important for chapter 4, but these are things that were from earlier on in the semester that I think you are likely to have forgotten by now. And we need to kind of just refresh you on those things, because if you don't know them, chapter 4 is going to be unnecessarily difficult. So the first thing is you need to be able to tell what an ion is, how to determine the charge for any ion using the trends of the periodic table, and you need to be able to tell the difference between a cation and an anion. You need to know names, symbols, and charges for polyatomic ions. Now, you were given a list towards the beginning of the semester of polyatomic ions to memorize. Now, if you haven't memorized them already, you are going to have to memorize them for this chapter, because we're going to be using them a lot, and you're not going to be given a list, the list of ions to refer to as you're doing this work and for your exams. So if you haven't committed them to memory yet, you need to do so now. You need to be able to tell the difference between an ionic compound, a molecular compound, and an acid. You need to be comfortable with nomenclature rules, meaning when we put two ions together, how do we do so to make it neutral? Meaning so there's no net charge unless you're otherwise told so. And finally, just some quick rules, just reminders about balancing chemical equations. So if you're looking at this list and you're like, okay, yep, I got all of these things, I feel really comfortable, then there's no reason for you to continue watching this video. You can just stop and go on to the next one because you're in good shape. However, if you're looking at this list and you're like, oh gosh, is this even English? Then I suggest continuing on, because I'm going to just quickly kind of review each of these things in hopes that it better prepares you to handle the chapter 4 material. Now keep in mind, aside from this video, it would be advantageous to review your notes, quizzes, whatever you have from chapters like 1 and 2 to get a more in-depth review of these concepts. But again, if you don't know these things, then chapter 4 is going to be unnecessarily difficult. Okay, so let's get started. Okay, so first let's take a look at what an ion is. So an ion is an atom or molecule with a net charge due to the loss or gain of electrons. So what does that mean? If I give you the symbol for sodium, this symbol for sodium right here is telling me that this sodium atom or molecule is neutral, meaning it has the same amount of protons as it does electrons. If I wanted to know what the ion for sodium is, I would write this. This is the ion that sodium forms. Now, this positive sign right here is meaning that sodium has a net positive charge of 1. So if this sodium over here had the same number of electrons and protons, but now it's positively charged by 1, what does that mean? What had to have happened to cause that? What happened is that sodium lost 1 electron, right? Because electrons are negatively charged. If this sodium over here, again, had the same amount of electrons and protons, and now all of a sudden it's positively 1 charged, that means it had to have lost 1 electron. So now there are more protons than there are electrons. So there's more positively charged things than there are negatively charged, and that's why it's positively charged. Let's look at another element. If we look at calcium, for example, the element calcium would be this. This is neutral calcium. There's no net charge. The ion that calcium forms is Ca2+. So this calcium is neutral. This right here is the ion. Now this positive 2 right here means that this calcium has a net positive charge of 2. So if this calcium on the left has the same amount of protons and electrons, the ion calcium, since its charge has a positive 2 charge, that means that it lost 2 electrons. Since it lost 2 electrons, it now has more positively charged things than it does negatively charged, and that's why it has an overall charge of positive 2. Now, if we look at a different type of element, for example, fluorine. This is the element fluorine. The ion that fluorine forms is F-. So this right here, this fluorine is neutral. It has the same amount of protons and electrons. This fluorine right here is the ion fluorine. And this negative charge means that it has a net charge of -1. So if this fluorine has the same amount of positive and negative things, and this one has a net charge of -1, that means that it has more negative things than it does positive things. Therefore, negatively charged ions are ions that have gained electrons. In this case, fluorine gained 1 electron, so it has more negatively charged particles to it. Now, if we look at another element like oxygen, this is neutral oxygen, has the same amount of protons and electrons. The ion that oxygen forms is O2-. So this oxygen has the same amount of protons and electrons. This oxygen is the ion because it has a charge. So this 2- right here means that it has a net charge of -2, meaning that it gained 2 electrons. Okay, so those are some examples of ions. Now, you might be asking, well, how did I know the charge of the ion that oxygen forms was -2, or that the ion that sodium forms was +1? Now, we know that by some patterns on the periodic table. So you may remember this from earlier in the chapter, but there are some facts in terms of ions. There's some elements that you can always count on to form the same exact ion, and there's other elements that can form multiple ions that are going to require a little bit more detective work. So first, let me tell you the ones that you can always count on. This column right here always forms +1 ions. Right here, this first column. Meaning you can take any element in this column and put a +1 in front of it, or behind it, sorry. And this is the ion that these elements form. Now we go one column over, these elements form +2 ions. So all these elements form +2 ions, meaning you can do the same thing. You can do Be, the ion Be forms is 2+. Mg, the ion Mg forms is 2+, and so on and so forth. Now, if we jump to the opposite side of the periodic table, this column right here always forms -1 ions. So all of these elements here will form -1 ions, meaning if we have F, the element F, the ion that fluorine forms is F-1. If we have chlorine, the ion that chlorine forms is Cl-, and so on and so forth. Now if we go one column over, these elements form -2 ions. So all of these guys form -2 ions. So what that means is if we have oxygen, the ion oxygen forms is O2 minus. If we have sulfur, the ion sulfur forms is S2 minus. Now, the transition metals here in the center, they're not as clear cut as these four columns are. They can form different types of ions. Some of them can form like multiple ions. Sometimes they'll be +1, sometimes they'll be +2, sometimes they'll be +3. It just depends on what they're paired with. So I'll show you how to figure out what kind of charge the ions, transition metal ions have later on in this chapter. Okay, so that is basically what an ion is. Now, let's talk about cations and anions. So cations are metals that have lost electrons. Therefore, they have a positive charge. Now, anions are nonmetals that have gained electrons. Therefore, they have a negative charge. So let's go back up to the periodic table now, and we'll take a look at some of the elements, the ions that we identified, and now we can classify them as a cation or an anion based upon if they are metals or nonmetals, or if they have a positive charge or a negative charge. So let's go back up here. So if we look at, let's just say sodium. We said, because sodium is in the first column here, that the ion that sodium forms is +1. Now, because sodium forms +1, does that make it a cation or an anion? Now, there's two ways you can answer this question. You can either look at the charge of sodium and relate that back to the definition, or you can see what sodium is. Is it a metal or is it a nonmetal? So we said that cations are metals. And sodium is a metal because it's located on this side, the left side here of the periodic table, and it has a positive charge. So for those two reasons, that makes sodium a cation. If we look at calcium, calcium's right here. We said that the element calcium, because it's in this column, forms a +2 ion. Now, does that make calcium a cation or an anion? Again, calcium is a metal and has a positive charge, so something that's a metal and has a positive charge is a cation. Now let's look at something on the opposite side of the periodic table. If we look at oxygen, oxygen is located right here in this column, so that means that oxygen forms a -2 ion. So would oxygen be a cation or an anion? If you refer back to the definition, we said that anions are nonmetals that have a negative charge. Oxygen is located on the right side of the periodic table, therefore it's a nonmetal, and we can see that the charge is -2. That was supposed to be an arrow, but that didn't work out. So because of that, because it's a nonmetal and it has a negative charge, that makes it an anion. Okay, so I think you kind of get the point here. But let me give you a little bit more difficult one. Let's look at a polyatomic ion, which I will get into more detail in later in this video. So this is a polyatomic ion called nitrate. So would this be a cation or an anion? Well, there is no nitrate on the periodic table, right? If you're looking, there's nothing that says NO3. So what you can do is you can look at the charge here. Is it positively charged or negatively charged? It's negatively charged. And what is something that's negatively charged? It's an anion. Likewise, another polyatomic ion is sulfate, SO4, and the charge on sulfate is -2. Would this be a cation or an anion? Again, it's not on the periodic table, so you can't tell by its location, but you can see that it has a -2 charge, and an ion that's negatively charged is an anion. Okay, so that was a quick overview of what an ion is, how to tell what kind of ion certain elements form by using the periodic table, and whether that ion is a cation or an anion. Now let's talk about polyatomic ions. So polyatomic ions are ions that are made up of multiple elements. So it's usually a nonmetal with a certain amount of oxygens coming after it, but not always. So some examples of polyatomic ions would be NO3, CO3, ClO4, SO4, PO4, OH, and etc. So in your textbook, there is a table, table number 2.5, and that table contains all of the polyatomic ions that you are supposed to have memorized. Now, some of them are ones that you just have to commit to memory. So for example, OH. OH is the polyatomic ion called hydroxide, and the charge of hydroxide is -1. I don't know of any tips or tricks to help remember polyatomic ions like hydroxide. It's just one of the ones that you have to memorize. But for the other ones that I've written down, there's kind of like a pattern on the periodic table that can help you remember how many oxygens they have, because some have 3 oxygens and some have 4 oxygens, and what the charges of these polyatomic ions are. So let's go back up here to the periodic table. So if we focus in on the nonmetals here, because polyatomic ions are a nonmetal with a certain amount of oxygens after it, there's kind of a pattern in the periodic table that can help you remember it. So first, let's kind of focus in on these 3 elements right here. Now, these 3 elements are the starting parts, the starting elements of polyatomic ions that you have to memorize. So all 3 of these, they have something in common. For polyatomic ions, all 3 of these, that's a little too thick, all 3 of these have O3 in their polyatomic ion. So this first one would be nitrate, this would be carbonate, and this would be borate. So the names you have to remember, but the names come from the elements that the polyatomic ion is made up of, so it really shouldn't be that complicated to remember the name. But one thing that can help you remember, okay, how many oxygens do these polyatomic ions have, is that they're located together like this, and they all have 3 oxygens. Now, another little pattern can help you remember the charge. So if you can just commit to memory that nitrate's charge is -1, you just go 1 more for carbonate and borate and you'll have their charges. So the charge for carbonate would be -2 and the charge for borate would be -3. So that is a little bit of a pattern to help you memorize how many oxygens these 3 polyatomic ions have and what their charges are. Now if we go down 1 row and we look at these 3 elements right here, they follow a similar pattern. And these are 3 more of the polyatomic ions that you have to memorize. Now just as these 3 right here had 3 oxygens after them, these 3 have 4 oxygens after them. So the names of these polyatomic ions would be chlorate, sulfate, and phosphate. They are all the element with 4 oxygens after it. Now, just as with these guys, these 3 up here, we had to remember that nitrate has -1, and then we just increase by 1 as we go to the left. We do the same thing with these 3. So the charge of chlorate would be -1, and we just increase by 1 going to the left. So the charge of sulfate would be -2, and the charge of phosphate would be -3. So you're just, the numbers go up, but the charges, I guess, go down because it's negative. Whatever way helps you remember it better. So this is just kind of a little bit of a pattern on the periodic table that can help aid you in memorizing these 3 or these 6 polyatomic ions. Just remember these 3 up here all have 3 oxygens. These 3 right here all have 4 oxygens. The charge of the one on the right is -1. Then you just count -2, -3 as you move to the left. And then again, the charge on the one on the right over here is -1. And then you just count -2, -3 as you move to the left. So this doesn't take care of the complete list, but it's a little trick that can help you at least remember 6 of them. But take a look at that table 2.5 in the textbook and practice that. Make flashcards, do whatever you have to do so that you can identify the name, you can write the formula, and you can write the charge for all of those polyatomic ions. Now, one last thing that I wanted to mention about polyatomic ions is that it'll be very helpful to you when we are balancing equations with polyatomic ions if you think of them as one unit. So if you think of this as, instead of like when you're balancing, if you're doing your bookkeeping method as nitrogen, oxygen, I have 1 nitrogen and 3 oxygens, that will work, but it's just a little bit more difficult, as if instead of thinking of this, think of it as one unit. So instead of saying 1 nitrogen and 3 oxygens, just think of it as I have 1 nitrate. So when you're dealing with polyatomic ions, this way just makes it a little bit more complicated, and thinking of it as one unit, so think of these as one whole piece that moves together, it can make balancing equations with polyatomic ions a lot easier. And we'll see that as we get more into chapter 4. Okay, so quick review on the difference between ionic compounds, molecular compounds, and acids. So an ionic compound is a metal, so something from the left side of the periodic table, plus a nonmetal, something from the right side of the periodic table. So an example of an ionic compound, probably the most well-known example, is Na, which is a metal, combining with Cl, which is a nonmetal, giving you sodium chloride. So this right here is an example of an ionic compound. Molecular compounds. Molecular compounds are a nonmetal plus a nonmetal. So 2 nonmetals. An example of a molecular compound would be water, H2O. Hydrogen being a nonmetal, even though it's on the left side of the periodic table, it really belongs on the right. Just for organizational purposes, it's on the left, but it's a nonmetal, combined with oxygen, which is also a nonmetal. So when 2 nonmetals are together, that is what a molecular compound is. Now acids. Acids are molecular compounds in the sense that they are made up of all nonmetals, but they always follow this format. They will always begin with hydrogen plus a nonmetal or a polyatomic ion. So some examples of acids would be HI, hydroiodic, HCl, hydrochloric, and if we did one with a polyatomic ion, we did HNO3, that would be nitric acid. So these 3 right here are examples of acids because they all begin with hydrogen, they're all made up of nonmetals, and the hydrogen and then the second part is either a nonmetal or a polyatomic ion. Okay, so that's a quick review just on the differences between ionic compounds, molecular compounds, and acids. That should still be relatively familiar to you, since we had to deal with those a little bit in the previous chapters. To do a quick review about nomenclature. Specifically, when we put 2 ions together, how do we do that so that whatever we're writing, the formula of whatever we're writing, has a net charge of 0, so there's no overall net charge. So let's look at an easy example first. So if we have sodium, which is a +1 ion, and chlorine, which is a -1 ion, how do I write these 2 together so that there's no net charge? Because right now there's a net charge of +1 on the sodium and a net charge of -1 on the chlorine. So when we bring these 2 together, because it's +1 and -1, the charges just cancel out, and we're left with NaCl, because the charge on the sodium is +1, the charge on the chlorine is -1, and these 2 charges cancel and equals 0. Okay, now let's say we had sodium again, which is a +1 ion, and we had oxygen, which is a -2 ion. Now if we look at the net charge right now, we have a +1 for sodium and a -2 for oxygen. So I have to manipulate something here so that the charges cancel out, Meaning, if I have a -2 on the oxygen, that means I want my sodium to have a +2, so +2 and -2 are going to cancel out because they equal 0. So how can I do that? Now when I bring these two together, for sodium, if each sodium is +1, and I know I want +2 to cancel out with the -2 of oxygen, I need 2 sodiums for every 1 of oxygen. And then if we look at just the charges here, so sodium's charge is normally +1, but we have 2 of them, so that gives a +2 charge, and the charge of the oxygen ion is -2. -2 and +2 is 0, so this right here is a compound with no net charge. Okay, let's try another example. If we had, let's try one with a polyatomic ion. So if we had potassium, which is a +1 ion, and we had the polyatomic ion nitrate, which if you remember is NO3 with a -1 charge. So here again the charges are +1 to -1. So +1 and -1 will already cancel each other out. So when these two come together, the formula would be KNO3. And now there is no overall net charge because potassium is +1, nitrate is -1, -1 and +1 cancel out, they equal 0. So this formula right here is perfect. We don't have to do anything else. But now what if we had potassium again, which is +1, with the sulfate polyatomic ion, which is SO4 -2. So we have a +1 charge here and a -2 charge here. So what can I do to the potassium so that its charge will be equal to -2, or there'll be a total charge of +2 that will cancel out with the -2 of sulfate. Well, if each potassium is worth +1, I can have 2 of them, which will be worth +2, which will cancel out with the -2 of sulfate to give me a compound with no overall charge. So it would be K2SO4. And if we take a look at the charges of potassium is +1, but we have 2 of them, so that gives me +2. And the charge of sulfate is -2. The -2 cancels out the +2, that equals 0, and that would be our neutral compound. Okay, so that's how we write formulas when we put two ions together. Just remember, like in this example, I had to add a 2 here as a subscript, right, for the charges to cancel out. I don't want to do this, put it as a coefficient, because that's something completely different. So remember, when you're dealing with charges and you're trying to get charges to cancel out to equal 0, you do that by manipulating subscripts. The last point that I want to make sure you guys understand is the difference between when we use subscripts and coefficients. So in the last example, when we had K2SO4, we had this subscript 2 in order for there to be 2 potassiums in terms of the positive and negative charges. So when we want the charges to cancel out to equal 0, we add subscripts. Now that is different from when we're balancing an equation to try to get the number of molecules of an element to match on both sides of a reaction arrow. When we balance, we use coefficients. So we'd put a number, like 2 for example, in front of this whole compound. And remember that when we put a coefficient, it affects the amount of potassium we have and the amount of sulfate that we have. So just be clear on the difference between a coefficient, which is used for balancing an equation, and a subscript, which is used for canceling out the ionic charges. Okay, so that is the last thing I wanted to go over on this kind of prerequisite video. So if you feel confident now with all of the concepts that I went over in this video, then you should be ready to move on to the material in Chapter 4.